Hello, Dr.
Hello, do you hear me? Hello? Ooh. Do you hear me? Just a minute. Me? Okay. Do you hear me?
I can hear you.
Okay.
Okay.
Okay. Can I start now? Do everybody hear me? Right. Hmm. I don't hear you. I Wait a minute. What about- Okay. Just a minute. Um, I'm not sure if I'm. Hmm?
Am I audible now?
Oh yes, I hear you perfectly now.
Okay, some issue with the speakers. So hello and welcome everyone. I am Devyani, and on behalf of Structural Steel Education Forum, I would like to welcome you all to our today's webinar on steel buildings in Japan and engineering. It is an immense pleasure and honor for us to have this talk delivered by Professor Taichiro Okazaki. Dr. Okazaki is a professor of structural engineering at the Division of Architecture at Hokkaido University. He holds a BE and ME in Architecture and Architectural Engineering from Kyoto University. He received his Ph.D. in Civil Engineering in 2004 from the University of Texas at Austin, USA. Prior to his appointment at Hokkaido University in January 2011, he was a researcher at the National Research Center for Earth Sciences and Disaster Prevention of Japan and assistant professor at the University of Minnesota, USA. Dr. Okazaki's research and teaching interests are in the behavior of steel structures, structural mechanics, and earthquake engineering. Dr. Okazaki is a member of professional societies, including Architectural Institute of Japan, the Japan Association for Earthquake Engineering, American Society of Civil Engineers, and American Institute of Steel Structures. Since 2021, he also serves as associate editor of the Journal of Earthquake Engineering. Before we begin, I would request all the participants, if interested, to leave their questions in the chat box, and after the talk, Professor Okazaki shall answer them. So I would now like to hand the stage to you to begin your talk.
Okay, thank you, Devyani. Thank you very much for the introduction. Good afternoon, good evening. My name is Taichiro Okazaki. It is my pleasure to be able to Okay. I'll talk a little bit about steel buildings in Japan. This is intended as a two-parter lecture. Today, I'll talk about the design and engineering aspect of steel buildings in Japan. January the 10th, I believe I have a second opportunity. I'll be talking more about the fabrication and construction. Okay, today I intend to talk about, go through my slides for about 90 minutes and leave something like 30 minutes for to answer any questions that you may have. Okay, I hope I'm being heard clearly. Please let me know if there's any issue. Now, today, this is the material I plan to cover. First, about the construction market of steel buildings in Japan, the historical development that led to today's steel buildings, the types of steel available in Japan, the codes and specifications, and then the big meat part, the design procedure, and some summary. Okay, first about the construction market. This is a chart showing the transition of the volume of building construction in Japan in terms of the total constructed floor area per year, starting from 1960 and to the right end going to 2022. I assembled the latest data, and the buildings are categorized by the primary material used. Okay, steel is highlighted by red. We have timber, reinforced concrete, and SRC. You may not, SRC is a very a unique construction method in Japan. It is short for steel cross reinforced concrete. It's a composite construction that was once very popular. Their popularity has diminished over the last 20 years. Now, there is masonry and other types of construction, but they are very, very small in proportion. Now, what I want to emphasize here is that steel is used is constructed in very big volume. We use more steel than reinforced concrete. Timber may appear very high up there, but the majority of the timber buildings are single house residences. So if you look at engineered buildings, steel is much bigger than reinforced concrete. And let's go into what kind of buildings use steel. Now, if these are both photos I took from very close to our university campus. The photo on the left became a hotel, and the building on the right-hand side became, it's not a big building, but it's an office. If you look in around downtown, my city is Sapporo, downtown Sapporo, or any urban area in Japan, you see many office buildings and hotel buildings constructed in steel. Steel is favored for parking. This is a big, what is it called? A shopping mall. And something like a good tenth of the building is parking, and basically the whole shopping mall is constructed in steel, and the steel is exposed in the parking area. Hey, many school gymnasiums from elementary through high school, most schools in Japan have gymnasiums, and those gymnasiums tend to be constructed in steel. Sometimes big gymnasiums would have up to the wall constructed in reinforced concrete, but still their roof would typically be constructed in steel. If you look into big industrial facilities, this is an example of a thermal power plant. These big buildings tend to be constructed in steel. Factories. Next time I'll be talking about fabrication shops. Many factories are constructed in steel. Okay, I didn't include an example today, but a big sports facility, big sports domes, they also tend to be constructed in steel. So steel is a favorite material for many different kinds of buildings. Typically, I mean, they are favored for long spans and tall, high rises, but they're also very popularly used for ordinary buildings. Okay, this is the view. I apologize. This is a chart I took from the internet, but this is public information looking into how domestically produced steel is consumed domestically. Okay, the left chart is from a couple of years ago, 2020. The right figure is the most recent data. In Japan, construct something like, what is this? Okay, I forgot the unit. This is, okay. 6 with 11 zeros. What would that make? 6, 0, 0, 0. I apologize, I forgot. Sometimes the numbers are shown differently in 0. 600 billion tons of steel is produced in Japan every year, and 37% is exported, and 63% is consumed domestically. And among the 63%, the primary industry that use steel is automotive, ship, infrastructure, and buildings. Buildings consume 30% of the domestically produced steel. And out of the 30%, this section highlighted in blue goes to steel buildings. HSS, plates, shapes, and rods and strips. So roughly 20% of the domestically produced steel goes to buildings. Oh, I wanted you to get a feel of how much steel is used in Japan for buildings. If you look into one way to look into the types of buildings is to look into the number of stories. This chart shows the transition in terms of the share of single story, second story, 3 to 5 story, 6 to 9 story, and up to high rises in terms of constructed floor area. There's not a huge change, but one thing about steel construction is that it's consumed, 50%, a good 50% goes to low rises. A single story typically means factory buildings. Second, 2 stories, much of this goes to small buildings. Some of them can even be houses. You might imagine steel to be used for high rises, but the proportion of steel that goes to high rises is not that big. If you look into look at the latest data of 2022, only 2% goes to very high rise, above 16 stories. Okay, that concludes the introduction about the construction market, how much of the construction market goes into steel buildings. Now, the second part, I wanted to go through the historical development of steel buildings in Japan. This is a table. Oh, I forgot to correct this. The first steel building ever designed by a Japanese engineer was constructed in 1885. I apologize for the mistake. This is not 1985, it's 1885. Okay, gradually different techniques developed, riveting, welding, and high-strength bolts. But the pivotal events that shaped steel building construction today are it is the 1923 Great Kanto earthquake. This year, 2023, actually marks the 100th year after this very large earthquake. Okay. The first high-rise building constructed in Japan is this 1968 Kasumigaseki building, more than 50 years ago. Up to that, this particular building, we didn't construct many high-rises in Japan. And more recently, we had this 1995 Kobe earthquake. So I want to walk through these 3 events to give you an idea of where our steel buildings came from. Okay, now before going to the 3 events, I'm revisiting that the transition of constructed floor area over the years and marking the 3 pivotal events: the Kasumigaseki building here, the Kobe earthquake here, and the Tohoku earthquake here. Now, looking into this, I'll discuss more in detail in the second half about the steel available in Japan. But the first industrial steel grade in Japan was introduced in the 1950s, and they were called the SS or SM grade. Rolled shapes became available in the 1960s, and in the second half of the 1960s, we began to form HSS, the square and round hollow sections. Now, in the 1990s, the newer steel grade was introduced. It's called the SN grade. And another important aspect is that this grade for HSS sections that we named BCR and BCP were introduced. Okay, so I'll revisit this later, but basically by the 1990s, the type of steel available today and the construction schemes available today were introduced to the market. Okay, now I'm going to talk about some of the pivotal events. Okay, let me skip this. The first, the 1923 Kanto earthquake, exactly 100 years ago. Now, at the time, steel buildings were constructed in Japan, but they were sought as a very economical method to form big office buildings. And the technology was imported directly from the US. And some of the the first large steel office buildings that were constructed in Japan or Tokyo were designed by American engineers. Now, these buildings didn't fare very well in this earthquake. They adopted the latest US design at the time. They didn't exactly collapse, but as you see in this photo, they underwent very, very severe non-structural damage. Okay? They didn't fall apart, but they experienced extensive damage to the exterior finish. Okay? Back at the time, the style was that they wanted every building to look like masonry in appearance, but those what appeared to be masonry were not detailed to carry lateral loads. The steel was very flexible and therefore allowed a lot of deformation, and the external finish were not able to follow through the large deformation. Now, basically, the U.S. engineers at the time did not know about seismic demands. And another example, a different building. I mean, these photos were taken 100 years ago, so they're black and white. Another example, the external finish, you see a lot of cracking marks. And it's very clear in this particular photo that the building is tilted after the earthquake. Oh, what's the perception was that steel buildings are not good for earthquakes, meaning that steel buildings are not very good for use in Japan. Other construction types fared much better than steel buildings at the time. Okay, steel buildings didn't collapse. It probably didn't kill a lot of people, but the severe damage to the external finish meant that they had to go through very extensive repair, or they had to give up they had to give up use of that building. Steel was denied, and after this Kanto earthquake in Japan, steel reinforced concrete, the SRC that I briefly mentioned earlier, and reinforced concrete shear wall became the system of choice. This building that I'm showing, the photograph I'm showing in this slide, this was a building that used very bulky reinforced concrete shear walls. And it survived the same Kanto earthquake with hardly any damage. So, in comparison, steel didn't look good. Okay, that was what happened 100 years ago. And another important outcome was that people were scared to build tall buildings anymore, so that a severe height limit was implemented. In Japan, buildings height was limited at 30 meters for a long time. It was later relaxed to 60 meters, but 60 meters does not go very tall. Okay. Now, one of the first buildings that broke that 60-meter height limit was this Kasumigaseki building, constructed in 1968. It's a long time ago, but it took 40 years after the Kanto, or 45 years to be more precise, after the Kanto earthquake to revisit this high rise. Okay, the Kasumigaseki building exceeded the height limit of 60 meters by a big margin. It was 147 meters. It has gone through several upgrades. I think it went through 3 or 4 major upgrades, and it still stands in the central Tokyo today. This particular building marked the beginning of high-rise construction in Japan. Now look at the photo on the right. When this building was going up, there was no high-rise in existence in Japan. And if you look closely at this photo, the buildings were 5 stories, 10 stories, basically limited by that the 60-meter limit. Now, about the same time, I want to introduce this particular building, the Century Royal Hotel, constructed in 1970. Not about the same time as the Kasumigaseki building. This stands at 69.3 meters, exceeded the 60-meter mark. Actually, this was the first building in Hokkaido, the region where I am at. The first building to exceed this 60-meter limitation. Okay, that qualifies as high-rise buildings in Japan. Oh, and to those of you who are familiar with steel design, this was actually the first eccentrically braced frame in the world. Eccentrically braced frames, or EBFs, were researched in the US in the late 1980s or 1990s. But this building was constructed decades before that time. Okay, sadly, it's been more than a century since this building was constructed. They decided to demolish this building next spring. Oh, by the way, I can also tell you that I make it my rule to stare at this building every day when I come to work. This building is very close to my campus, and if you compare this photo to the left and the elevation to the right, you can see where the eccentrically braced frames are located. It's located along this tower segment. Next, I want to skip to the Kobe earthquake. I'm going to show you some other shocking photos. To the left are extensive damage to the expressway in Kobe. The top left photo shows what people would call the elephant foot buckling, and the buckling deformation was so severe that it cracked this bridge pier. And the bottom left, it went worse. It completely collapsed the bridge pier. And this is a steel construction. To the right, this is a steel building. The connections performed quite well, but look how badly the column is deformed. The Kobe earthquake damaged many steel buildings and facilities. This photo assembles damage to steel braced systems. Okay, the diagonal braces tend to be the first structural members to experience damage in an earthquake. Looking at the bases of columns, the left photo shows the columns that seems to have gone a lot of good plastic deformation, a ductile behavior. The photo on the right side shows how the column bases have failed. The photo on the top right shows that anchor rods went somewhere, or the column was pulled out of the anchor rods. And the photo on the bottom right shows how the anchor rods have been extended, and the mortar underneath this base plate is completely crushed. And these are other shocking photos. The photo on the left is a not very significant building. The members are light, meaning that they probably dated many decades by the time of the earthquake. But the building is badly tilted. The photo on the right-hand side, it was a very new construction at the time of the earthquake. It used very thick and heavy members. The photo shows how this very thick column had fractured across the entire cross section. Okay, there were many different variations of damage that people realized after the Kobe earthquake, but the most extensive and common damage was this one. We're looking at the connections between the beams and columns. The photo on the top left shows the column that was torn across the cross section. The other photos show damage to the beams, the connections between the beam to the column. The bottom left shows a beam that's completely separated from the column. Okay, the two photos on the left seems to have been due to poor quality of the weld. I suspect that the welding was done by fillet welds rather than the complete joint penetration and groove welds. The photo on the right-hand side are the ones that was very shocking at the time. Now, let me spend some time to explain this. Okay, many buildings experienced this damage. What we see is in many steel buildings, the rigid connection between the beam and column fractured at the bottom beam flange. To take a very close look, do I have? Okay, here. This fracture tends to happen near the weld cope. To achieve a complete joint penetration groove weld between the beam flange and the column, we would want to introduce a weld cope to allow continuous welding across the beam flange. Now, but people realize that because of the cope, or in this particular example, this presence of the weld cope seemed to have been the direct cause of the fracture. In this case, the fracture probably initiated at the end of the weld cope right here, and immediately fractured along across the entire beam flange. And after the bottom beam flange was separated, the fracture started to go into the web. Now, this type of failure was observed in many different buildings. Another example, looking at the bottom beam flange connected to a column. Okay, so similar to the example that I just showed you, the fracture seemed to have started at the end of the weld cope. Another example. In this example, this case, the connections seem to have done a little better because we see good evidence of plastic deformation in the beam flange. Anyway, so people realized that the welded connection between the bottom flange and the column is where we really need to pay attention to achieve steel buildings. Okay, I'll talk about this a little more next time, but I wanted to give you an idea that a lot of this experience, or what we do the design and construction of steel buildings is established based on all these experiences in the past. Another example of a steel building constructed very close to where I'm at. The left photo shows the steel building being constructed, and the right photo shows the building after construction. So once the building is constructed, it's hard to tell whether the building is constructed in reinforced concrete or steel, but many of these these office buildings in Japan tends to be constructed in steel. Okay, moving on to the next subject. The types of steel that are available in Japan. Now, this may be a little, this is a somewhat detailed information, but a unique feature that I want to convey today. Now, there are two types of steel that are used for buildings in Japan. One is the type that are defined in the industry standard, and the other, and there's another category that we call the minister approved steel that is not part of the industry standard, but are approved by special permit. Okay. The industry standard is available in most or maybe all countries in the world. The industry defines a grade, and material is supplied in compliance to that grade. Now, in Japan, we have this building standard law of Japan that lists all the different types of steel that are permitted for use in buildings. And most of those are taken from the industry standard. We call this the Japanese Industry Standard, or JIS for short. Now, but the newer steel tends to be outside of the JIS. They are not a part of the JIS, but they are approved company by company and factory by factory by the Ministry of MLIT, or basically the Ministry of Construction. So this may be one takeaway to know about Japan. We have two different types of steel. One that are part of the industry standard, and the other that are not part of the industry standard, but are permitted by special approval. Okay, with that in mind, I'm going to walk through the most common grades of steel in Japan. The first and the original grade is this SS. There are actually 3 different grades, but today we don't see this SS 490 or SS 540 on a regular basis. Okay. There's this original SS grade, but a somewhat improved SM grade. The difference is that SS is the basic grade, and SM has a little tighter requirements to secure weldability. Now, this SS and SM were the first 2 grades for building construction. Okay. The numbers 400, 490, 540, these numbers list the strength grade. Okay, I'll talk more about what these numbers and symbols mean, but right now, please recognize SS and SM. Now, the new grade was introduced in the 1990s, and we call this the SN. Okay, these SS, SM, and SN are the 3 fundamental steel grades in Japan. Now, what I highlight in yellow are the particular grades that are commonly used. Now, the other ones are not very commonly used. They're listed, but not very commonly used. Okay. We have specific grades for hollow steel sections, for rounds and for a square and rectangular. Rectangle. The rounds are called STK and the square are called STKR. Now, STKR were the original square SSS. Hey, you don't need to memorize all this. I mean, unless you're designing in Japan, but I wanted to give you a feel of the steel that are available in Japan. Now, SS was the original grade that was established in 1952 following the British standard at the time. So there are a lot of similarity between the British standard at the time and SS. Now, later, or more recently, we introduced the SN steel in 1994, primarily to meet the requirements for seismic design. Okay, the two objectives were to reflect the advancement in manufacturing and quality control, and second, perhaps more importantly, to include ductility requirements. Now, the ductility requirement is specified by what we call the yield to tensile strength ratio. Okay, if the tensile strength is somewhat higher than the yield strength, that means that the steel tends to have good ductility. But if the yield strength is close to the tensile strength, then the ductility tends to be poor. So controlling the yield to tensile strength to be lower than a specific value is an effective means to control ductility. The American standard does something does the same, and the European standard also introduces this yield to tensile strength ratio for the same objective. Now, this SN steel has three subclasses. It's A, B, and C. And basically, B is better than A, and C is better than B. Or C is the most expensive, A is the cheapest. Now, the SN class A is basically the same as SS400. They are not, similar to SS400, they are not certified for welding. The class B is the most common type used. So ordinary beams and columns would use SN class B. Okay, SN class C is for a special use. They have the through thickness properties certified, and they are intended for special use that I plan to talk in the next lecture, the next time. Okay, I walked you through the industry standard steel. Next, let me walk you through the special, the minister approved steel. Okay, the minister approved company by company or factory by factory approved steel is used very commonly in Japan in the form of square HSS. Most of the buildings in Japan use square HSS for columns, and those columns would be either this BCR or BCP. Okay, so other than this very commonly used BCR and BCP, we have the higher strength grade and TMCP. TMCP, I forgot what it is short for, but this is a scheme to control the strength of steel or achieve high strength by controlling the heating and cooling cycle. Okay. these are examples, and we have many minister-approved steel. Okay, I mentioned that almost all steel buildings in Japan use square HSS, and there are two types of manufacturing schemes for HSS. One is the form from round, and the other is form square, weld square. Okay, the first one would bend a flat plate to form a circle and weld where the plates meet. First form a circle or a round shape. Afterwards, squeeze from four sides to achieve a square shape. And this is the first type of manufacturing. And the HSS formed in this scheme is called BCR in Japan. The second type is the bend plate at the corners and weld where the ends meet. I would believe the same process is used anywhere in the world, but the difference is that Japan does these two manufacturing schemes very extensively. Let me mention the designation rules between the industry standard steel and the minister-approved steels. I walked you through some of the most common steels, the SS, the original one, and SN, the more recent one. For SS and SN, the numbers mean the minimum tensile strength. Okay, so we have the strength grade 400 and 490. A, B, C are the subclasses that I mentioned. Now, for the minister-approved steel, there's a different designation rule. The letters at the first would mean the type of steel or the type of manufacturing. The numbers, unlike the industry standard steel, these numbers 295, 235 mean the minimum yield strength. Okay, the sigma Y as opposed to sigma U. Okay. Now, I'm not going to explain the whole thing, but give you an idea of the material properties. Okay, we have the SS steel, the SM steel, and the SN steel. These are the type of steel available. The yield strength and the tensile strength. The yield to tensile ratio is specified only for the steel that are rated for ductility. That means the SN Class B and Class C steel. These are the steel that would be used for primary members that resist earthquakes. Okay, the old or original grades did not have Sharpie requirements. The higher end or the more recently developed steel has Sharpie requirements. The same list for HSS and the minister-approved steel. One thing I want to mention, okay, the difference between the old HSS grade and the new HSS grade is that the tensile ratio is specified to the new grades, not in the old grades. Okay, one important quality control scheme for steel is weldability. The American Welding Institute and the International Carbon Equivalent is written in this equation, but for some reason, Japan uses a different definition of carbon equivalent. We have two types. They're named differently, but they both serve the same purpose, to control weldability of steel through chemical content. And we know that carbon is good to have in steel, but if you have too much carbon, you tend to experience cracking as you weld the steel. So you don't want too much carbon. And all the other chemical components are transformed into carbon equivalent. These other chemicals are, some of them are good to have, but if you have too much of them, you degrade weldability. Okay. So this is the list of chemical requirements in terms of the each element and weldability. Looking into SS, SM, and SN. The older steel tends to have more relaxed limits. The newer steel, in particular SN class B and C, has tighter requirements. The original steel were very relaxed. Okay, looking into HSS. So the main thing I wanted to pay attention is that the SDK, SDKR are the old HSS. The BCR, BCP are the new HSS. The chemical limits are much tighter in the newer grades. Another aspect is that in the new square HSS grade, there's a limit for nitrogen. If you have too much nitrogen, you tend to ruin the corner properties of steel. Okay, so the nitrogen limit was not there in the older grade, but there's a tight limitation for the newer HSS. Okay, though there's a lot of different steel grade, and engineers can, the industry has provided these very handy handbooks to aid in choosing which steel to use. The two, the red one and the blue one are provided by the steel manufacturers. I list the link to find the PDF versions or the web versions of these books. But these two tend to serve the commercial purposes of the steel manufacturers. So they have a big list of materials. The green book on the far right is provided by the Steel Fabricator Association. So they narrow down the list to what engineers tend to use. So they omit the very specialty steels. So this green one tends to be the most handy. Anyway, if you open these books, there is a chart or tables that summarizes the mechanical properties and the chemical content of each different steel grade. This is for SS and SM, and this is for SN. The same book also includes many charts, including this one, to list all the different steel dimensions available. This is the table for I-section beams, and this is for the square HSS. Okay, that concludes part 3. Gradually moving to the design part of today's talk. Let's go into codes and specifications. Now, the design methodology in Japan is actually quite complicated because different books, many different books are provided by different entities. And the one book that has absolute authority is the one that is prepared by the Ministry of Construction. Okay, the Ministry of Construction maintains the building law of Japan. Okay, this is the built-in law that any engineer has to adhere. The law is supplemented by many sub-documents. Now, the second entity is the Japanese industrial standards. I've already mentioned this. The JIS specifies the materials and some building standards. There's also the local jurisdictions, big jurisdictions like Tokyo and Osaka prepare their own design recommendations. And there's also a different category of design requirements for the government office buildings. Okay, going down the list, we have the Japanese Society of Steel Construction, sponsored by the steel industry, that prepare industry standards and state-of-the-art reports. We also have the Architectural Institute of Japan, which is the professional society for engineers and architects, which prepare the state-of-the-art standards and recommendations. Okay, on top of this, the industry in Japan is very active. They come up with very innovative ideas, and they provide design guidance for the ministry approved technology. Okay, if you invent something, you can promote once that technology is approved by the minister. Okay, what's happening here is that the building law in Japan is a fixed law. I'll talk about this later in the coming slides. The law was defined in the 1950s, and there was one update in 1980s, but after that, there's hardly been any change. Okay, the law that was activated in 1980 defines how buildings are designed in Japan. Of course, it's been 40 something years. There's a lot of newer technology, but it's not incorporated in the law. So that these different entities with different interests come in to try to chip in and give ideas on how to do better. It may be the local jurisdictions, it might be the steel industry, it might be the professional society, it may be individual companies. Now, but among these different codes and specifications, these two entities or bodies are tend to have the most authority. The left one, of course, because this is the building standard law. This is the law. Everybody has to follow the law. Now, on the right-hand side, we have the professional society, or where all the academics chips in. Okay, the academics come together to assemble and put together minds to come up with to explain newest research results and explain design rules in a better way. Okay. So what's happening in Japan is that the law is the law, and the academics are academics, and there's not a direct connection between these two bodies. Okay, this the AIJ, or the academic documents. Okay, they tend to be the most updated, and therefore they are referenced by engineers to supplement what the law requires. It contains the state-of-the-art academic knowledge. This is where research contributes. So I, for one, do research, and one direct thing that I have in mind is to contribute to the academic documents prepared by AIJ. Okay, I will be talking about the level 1 and level 2 design that's defined by the law. The AIJ documents contribute to level 1 requirements, but it doesn't address the level 2 requirements. Okay. Okay, what do the academic society do? We organize design rules, the three fundamental design rules. They probably are acknowledged anywhere in the world in the realm of steel design. The allowable stress design, plastic design, and the limit state design, or LRFD. Okay, we pay attention to all three design rules, and these documents are frequently updated. Okay, these the hand points to where I am a part of. Okay, the academic society prepares many other design recommendations for composites, for fire, for connections, and for tubular structures. Okay, these documents are updated every 5 to 6 years to provide or share the state-of-the-art knowledge with the community. One area of emphasis is connections. Okay, we have these recommendations for connections, and we have supplementary documents that details bolted connections and welded connections and column-based connections. Okay, the AIG also standardize the fabrication and construction requirements. Okay, we have 2 thick books, one for erection and one for fabrication. And these 2 books are very heavily referenced by regulations. Okay, the AIJ Academic Society goes into really the high-end techniques. One book that probably doesn't exist anywhere else in the world is how to design buildings with supplemental damping systems. Lightweight steel structures, and we also have a series of books that summarizes state-of-the-art guidelines for stability and sustainability. By the way, I'm also part of this last one on sustainability. Okay, I probably covered a lot of grounds, but these are some of the things I wanted to emphasize. The AIJ steel documents have been updated quite frequently, and this is because our academic community has been very active. And one aspect of what we do is that we have not converted to LRFD like the rest of the world. This is primarily because the design earthquake load is strictly governed by our building law of Japan. And because the load is defined by law, it's very hard to update the load requirements. And if you cannot control the load requirements, then we cannot, it's hard to, or it's nearly impossible to discuss the reliability of our design. Now, this is probably where we are stuck at in converting or advancing to LRFD. Now, I mentioned that we have a lot of documents, but I do personally feel that we need more coordination because we publish a lot of books, but we don't have a single book that covers all. And we do feel frustrated that the building law does not change, but we probably need to accumulate convincing evidence to tell them that, okay, this is how we can do better, and this is how this is why we need to change the law. Okay, now next, moving to perhaps the most important part of today's lecture, the design procedure in Japan. Going back a little bit of the history, okay, the building standard law is what dictates our design rules. It was first introduced in 1919. One good thing we can say about ourselves is that after experiencing the Kanto earthquake, the earthquake 100 years ago, we were the first to implement seismic requirements. Back at the time, we said that the seismic coefficient is 0.1 for a safety factor of 3. So what the high minds at the time said was that the base shear coefficient is basically 0.3. Okay, well, the 0.3 means the safety factor times this coefficient of 0.1. And this 0.3 is still used in our building requirements today. Okay, there was a name change. The urban building law, the law that was only covering big buildings, big cities in Japan, was now spread to all buildings in Japan in 1950. And in 1950, we introduced this concept of sustained loads and temporary loads. Sustained loads are basically live loads that do not go away throughout the life of the building. Temporary loads mean earthquake and wind loads that may act for some period of time, but are expected to go away after a while. And we always tend to be visited by major earthquakes, 1968, 1978, which prompted a big change in the law. In 1980, we introduced what we call the two-level design method. We also call this the new seismic design. And this method that was introduced in 1980 is basically what we continue to do today. Okay, and in 1995 Kobe earthquake, I mentioned earlier, the buildings that were constructed before 1980 fared badly, but buildings that were built according to the new laws introduced in 1980 fared quite well. Okay, that's where we build confidence that this 1980 rule seems to be good and maybe good enough. So afterwards, there has been minor revisions, but this 1980 rule still survives today. Okay, what is this two-level design method? There's a level 1 design and level 2 design. Okay, level 1 design says that the building should withstand sustained loads and temporary loads, or in terms of earthquakes, the temporary loads mean earthquakes that are expected to happen a couple of times during the life of the building. The building should survive such earthquakes with minimal or no damage. And such requirement is addressed by allowable stress design. Okay, level 2 design, which was introduced in 1980, says that the building should not collapse nor risk human life even during severe earthquakes. Now, this is the more modern requirement. This level 2 requirement is addressed by one of 4 design routes. I'll talk about this next. Now, there are buildings that do not follow this level 1, level 2 rule. And those are buildings that exceed the height of 60 meters, or buildings with irregularities. So special buildings. Now, special buildings are required to convince a review board with evidence, including time history analysis. But the vast majority of buildings, ordinary buildings, follow this two-level design method. Now, let's talk about level 1 first. This level 1 is addressed through allowable stress design. Okay, allowable stress design. I know it's archaic. It's been around probably for a good century. The requirement is that the computed stress should not exceed the allowable stress. And this sigma not exceeding F should be checked for all fibers of all sections of all members. The computed stress is an outcome of elastic analysis conducted through conducted on the basis of the design loads. The allowable stress is defined by the material strength, the limit state governed by either yielding or stability, and safety factor. Okay, I think this is common knowledge to the whole world, but let me walk through the specific procedure in Japan. Okay, elastic analysis, there's nothing to it, but let me talk about the design loads in Japan. Okay, these are the fundamental load combinations. There are the temporary loads and sustained loads. Okay, temporary loads, I'm sorry, this is flipped. The top one should be sustained and the bottom one should be temporary. Okay, so this is sustained. Sustained load means basically dead load plus live load. And if you are in a very heavy snow area, you should toss in some of the snow load. There are three different temporary loads: snow and wind and earthquake. Okay, and in heavy snow areas, you do need to consider the combination of dead and live load, yes, being there, and earthquake hitting during the winter time. Not the full snow load, it's reduced, but including all four loads. Okay, what do you do in terms of analysis? Okay, you apply the snow load, dead load, live load, and you may have earthquake load. You do linear elastic analysis. You will need to do the check for all beams, all columns, all cross sections, all fibers. Say I'm looking at this particular critical section or critical fiber at section A and section B. Okay. You have to do checks for sustained loads and for temporary loads. Now, the allowable stress is 1.5 times higher for temporary loads than it is for sustained loads. Okay. Temporary loads may happen, does not, sustained loads, you have to survive throughout the entire life of the building. So you are, there's a safety factor there. But for temporary loads, we would remove that safety factor. Therefore, the allowable stress is higher for temporary loads. You do need to do the check for sustained load combination and for temporary load combination. Okay, for this critical fiber at B, the check for the load combination, the sustained load combination may govern because this is closer. And for temporary load requirements, there's a bigger separation between allowable stress and the design result. But for critical fiber at A here, where earthquake is expected to have more effect, it's maybe hard to tell whether the temporary load requirement will govern or the sustained load requirement will govern. Now, let's look a little more detailed into the loads, particularly the earthquake loads. To the left is the seismic hazard map, the map of Japan. Okay, skipping the details, the darker red means high seismic risk, and blue or green means low seismic risk. So there is disparity in seismic risk in Japan. This area, the far northeast has high risk, but there are actually parts of Japan where the seismic risk is relatively low. But if you look into recent history, the two most recent major earthquakes in Japan, one in 2016 and one in 2018, they happen in areas where the risk is recognized as low or not too high. Therefore, in Japan, we do not use this seismic hazard map very often, and we use this map on the right, which the darker means larger earthquake load, and the lighter or the white means smaller earthquake load, which is far less detailed compared to the map, the seismic hazard map on the left. And the difference in earthquake load between high seismic and low seismic is not much. Okay, looking into this pink or red region covered here, the seismic load is 1. In the low seismic regions, like here, the seismic load is 0.8. The difference is only 20%. Oh, in Japan, even those regions where the risk is relatively low does not mean absolutely low. And that is recognized by the small difference in the earthquake loads across the country. Now, the load distribution is computed like this. K indicates the load distribution, but in design, what we directly compute is the story shear force, Q, as a proportion of the total floor weight resisted at that story. Okay, at this third story, the weight of the third floor, fourth floor, fifth floor, and sixth floor are sustained. The story shear is defined as the proportion of the weight sustained at that story. So that if you want the earthquake load, you could back calculate the earthquake load as the difference between the story shears. Okay, so the earthquake load is proportional to the floor weight. I think this is common in anywhere in the world, but then how is this the proportion factor CI calculated? Okay, this is a product of the seismicity zone factor that I showed earlier. The difference is only between 1 and 0.8. Okay, this Z. We account for soil amplification, the vertical distribution, and the standard base shear coefficient. The standard base shear coefficient in Japan is 0.2 in Japan for level 1. The soil amplification is a function like this. It's a function of the fundamental vibration period of the building. Okay, there is different amplification depending on whether the soil is hard or soft. Soft soil has a more amplification. Hard soil has less amplification. There is a very unique vertical distribution factor introduced in 1980 that looks like this. It looks complicated, but a very well thought vertical distribution across different floors. And in Japan, the fundamental vibration period of buildings is computed as a function of the height in meters. So if you have a building that is 10 meters tall, the period will be 0.1 seconds. I'm talking about steel buildings. Concrete buildings is expected to be stiffer. Okay, I walked you through or gave you some idea of the design loads. Now let's look into the allowable stress of these three aspects. Now first, about the material strength. The material strength is written as this capital F. Now there's a unique rule in Japan that this design basis material strength is the smaller of the yield strength of the steel or 70% of the tensile strength. Okay, the 70% of a tensile strength, if this is smaller than the sigma y, basically this concept is to place penalty for less ductile steel. Okay, this material strength, that is the fundamental material strength used in design, is the smaller of the minimal specified yield strength and 70% of the minimum specified tensile strength. And that standard material strength is defined for different grades of steel like this. Okay, the grades are listed here, but I show in red and blue only the ones that are very commonly used. The gray ones, forget about it because people hardly ever use them. This table is for the industry standard steel, and we have a different table for the ministry approved steel. And among the ministry approved steel, the square HSS are used for almost all steel buildings. And this is the material grade. Now, once you have the standard strength, the allowable strength would be calculated through these equations. Okay, if you have a member in tension, the allowable stress is the standard strength divided by safety factor. For sustained loads, the safety factor is 1.5. For temporary loads, including earthquakes, the safety factor is unity, 1. Okay, for compression members, the allowable stress is dictated by buckling. So the stress is a function of the slenderness ratio. For flexure, the strength is dictated by lateral torsional buckling of the member. Oh, we have some function. Hey, I write out the allowable stress for sustained loads, but for temporary loads, all you do is to replace this 1.5 by 1.0. And we have the set of equations that look like this. Okay, this part may have been boring, but this is our interpretation of the allowable stress design. Okay, let's look into the bigger picture of the design process in Japan. First, all buildings are required to do this level 1 design, which is to check for allowable stresses. And then the allowable stress design is the older design rules. And on top of that, in 1980, we added these newer rules. The allowable stress design, or the level 1 requirements, would dictate the proportion of members. And once we check, we proportion the members, there's a check for drift. We check for the level 1 design loads that the story drifts are within 1/200. And afterwards, we check for the ultimate strength for larger loads. And depending on the scale of the, beyond here is what was introduced in the 1980. Depending on the scale of the building or the simplicity or complexity of the building, you may go to the simplest route 1 to the more complicated and complete route 3 design. The most buildings would go to route 3. But the simpler ones could go use route 1, there's a route 1-1, route 1-2, and route 2. Shorter buildings, regular buildings, simpler buildings go to the left. Bigger buildings, more complicated buildings go to the right. And for Route 3 and Route 3, there's a requirement to have to check for conformity, or have to have a third party check whether your design results conform with all requirements. Oh, I'm listing some of the primary elements of the 4 different routes, but skipping the details. Okay, the Route 1 and Route 2 actually use allowable stress design. It sort of repeats the allowable stress design, but it increase the seismic loads from the base shear coefficient of 0.2 to 0.3. Okay, now you are asked to do capacity design for connections to prevent connection failure. There is some ductility requirements in terms of slenderness and width to thickness ratio of the members, and some additional check to address the inferior ductility of the cold form HSS columns. Now, I mentioned ductility. That is basically checked by the B over T with the thickness ratio of the cross-sectional elements. Now, for level 1 design, you can stay with what we call the rank C. But for level 2, you may be required to use rank B or rank A members. We have these set of B over T ratios or limits for I sections used as beams, I sections used for columns, HSS sections used for columns, and all different section types. Now, going back to this list, let's look into what this Route 3 means. Route 3 asks to check the ultimate lateral strength and also check what kind of energy dissipation mechanism your structural system would form. QUN is the capacity. The capacity is a product of this modification factor, amplification for irregularity, and the story shear coefficient. The story shear coefficient is 1.0. I mentioned that for allowable stress design, the base shear coefficient is 0.2 or 0.3. This is amplified to 1.0 in Route 3. But this amplified story shear is reduced by this modification factor. This modification factor, D of S, is the heart of Route 3. Okay, for we do pushover analysis to compute the story shear demand. Oops, okay. I made a mistake. This is smaller or equal to. The demand has to be bigger than, the capacity has to be bigger than the demand. Okay, we do elastic plastic pushover analysis to compute the demand and make sure the capacity exceeds that demand. Oh, sorry, this is correct. Sorry, QU is the capacity. Okay, QUN is the demand. And we do pushover analysis to compute this QU. This DS is computed based on the type of structural system, the expected mechanism, and the B over T of beams and columns, and slenderness of braces and such. Okay, the rule to compute these of S is a little bit convoluted. but let me explain how it's done for moment frames. Okay, we look at the ductility rank, or we first use this table to define the ductility rank of the moment frame. It may be A, B, C, or D. D doesn't happen very often. But if you have a very ductile A system, then the reduction factor, D sub S, is 0.25. This means that the base shear coefficient is reduced to 0.25. If you have a less ductile system, then the base shear coefficient is 0.35. How do we compute the ductility rank? You look into each story to check whether the mechanism is dictated by a rank A member, or rank B member, or rank C member. The rank A, B, C is according to the B over T category that you belong to. Let me go back. This list. Okay, this is the rank A member, rank B member, rank C member, decided by the B over T ratio. Okay, in this illustration, I show a case where the mechanism is, I show a mechanism where the plastic hinge is formed in the B, and the B, formed in the beam, and the beam is rank B. In this particular case, the mechanism is dictated by a rank B member. And you do this check, and for each story, and you compute the net resistance within that story that is resisted by a rank A member and a rank C member. If you have a lot of rank A members, then you win ductility rank A. If you have a lot of rank C members, you're bumped down to rank C. And such procedure is relatively easy for moment frames, but it gets a little complicated for brace frames. For brace frames, the ductility rank of the member is dictated by the slenderness of the braces. And we do something similar, looking into the proportion of rank A braces, rank C braces. Also look at the proportion of lateral load resisted by the braces over the load resisted by braces and moment frame combined, and use this table. Okay. Beta means the proportion of lateral load resisted by braces. So beta 0 means moment frames. So if you have a moment frame, you basically go to this 0.25, 0.3, and 0.35, the same values that I showed you 2 slides ago. If you have braces, then the table gets more complicated. But basically, if you have a very, very ductile brace, you are rewarded the factor is 0.25. If you have a ductile system, a less ductile system, very bad braces, then it might go as bad as 0.45. How does this come into the picture? And I'm showing an example of an elastic plastic pushover analysis. Okay, the loads, the vertical gravity loads are all here, and then you increase the lateral loads in proportion. These green lines mean the story shear versus story drift at each different story. Okay, the first story is obviously the strongest, so it comes here. That top story is the smallest, and the story shear is the smallest, so it comes down here. If we do this pushover analysis, and most engineers say that when there's one story that reaches a 0.01 story drift ratio of 0.01, that's when I check my ultimate strength. Okay, I've computed the ultimate lateral strength for my first story, second story, third story, and so on. And for each story, I check whether the capacity, the computing capacity, exceeds the requirements, the required story strength. And if the capacity exceeds the requirements for all stories, then my design is fine. There's a second check. Engineers would further push until one of the stories reach a story drift ratio of 0.02. And under this state, they check to make sure that the energy dissipated mechanism is according to what he or she believed the system was designed for. Okay, like this. Push further to here to do these two checks. Okay, so let me try to summarize the design procedure in Japan. There's a two-level design procedure. There's a level one. The intention is to limit damage under frequent earthquakes, but this is basically the member proportion rule, which is based on allowable stress design. I didn't talk about this, but there are also fundamental quality control requirements and fundamental design rules. Level 2 is heavier on analysis. Okay, there's a drift check based on still level 1 loads. There's a more stringent ductility rule, which is a function of B over T. And there's the elastic plastic pushover analysis that I mentioned to check that the lateral strength and mechanism conforms to the requirements. So let me add a couple of comments. Some of you may have, might have been shocked that the procedure is quite simple. The fact is that the Japanese design procedure has remained mostly unchanged since the 1980s. And what does that mean? Back in the 1980s, we didn't have computers, so the procedure was meant for hand calculation. And from the current point of view, the procedure is not necessarily suitable for computer-based analysis and design. Now, the code does not cover connection detailing rules, and I mentioned elastic plastic analysis, but the building standard law does not define the ultimate strength of members and connections. It certainly does not include latest research. And these are precisely the areas where the engineers look into the academic documents to learn more about how to do good connection design, how to evaluate the ultimate strength of members and connections to feed into the computer analysis. Furthermore, the latest technology are not implemented in the code. They are implemented in the practice through special minister approval. The approval might be done per project or per technology. This is a very unique system that proved to be more effective than patents in the Japanese construction market. Now, some of you may be aware that buckling restraint braces, BRBs, eccentrically braced brace frame systems, twist-off bolts, these are technology that are invented in Japan. Now, these Japanese inventions are not implemented in the codes. Some of them are, or actually most of them, are recognized by minister approval. Okay, the nonlinear time history analysis this is taught in college education, but the only case where this is used is to check for story drift in high-rise buildings and special buildings. Now, I'm trying to convey some of the frustration I feel and give you a sense of where I feel that the Japanese steel building should be heading. Oh, future directions. I think we need better coordination between different entities that would include government, industry, and academic to better assemble design rules that are scattered over many different sources. We should develop design methodology that take advantage of latest analysis methods, improvement in quality control, and the ever-advancing information technology. I think that, there is more and more pressure to improve productivity of the industry. Okay, I'm coming close to the conclusion of today's lecture. Let me try to summarize. Okay, I started off by explaining that in Japan, steel has enjoyed a very large share of the building construction market, perhaps more, a bigger share than any other country in the world. Now, but somehow the material and construction scheme has remained rather unchanged since the 1980s. The material and the construction technique, I'll discuss more next time, has been rather consistent since the 1980s. There has been advances, and I'll talk about that as well next time. The big problem is that the design procedure has remained rather unchanged since the 1980s. Especially after the Kobe earthquake, this 1980 change proved to be effective. That's a big example that our design procedure has been effective through many major earthquakes. But as I tried to explain towards the end, we do see opportunities for improvements and advances. Okay, I talked a lot, but I hope there have been enough takeaways. Thank you very much for your attention, and I'll be glad to answer any questions that you may have come with. Okay, let me stop my slides. How do I stop? Okay.
Well,
Okay.
thank you, Dr. Okazaki. It was a very insightful, detailed, and educating presentation. And as of now, we have not received any questions in the chat box, but anyone who wants to ask any question can also raise their hands. We will unmute them. And yes, we do agree with what you summarized, and for the future directions, hope to see those being implemented in India as well. So we don't have any questions for today, but we look forward to your next presentation, which is on construction and fabrication of steel structures in Japan. Yes, okay. So we have a question here. Why limit state method is not under current practice in Japan?
Yes, this is actually an issue that I'm personally working on. Okay, I don't have a slide or black. I mean, it's a pain to write on the whiteboard on screen. If you look into how LRFD was developed, you have to analyze the reliability of on the structure side, and also the reliability of the load side. Okay, the scatter of structural performance is due to scatter in the loads and also the scatter in the structural performance coming from scatter in material, the material's strength, and also the quality control and such. Okay, you have to look into all of that and come up with and analyze the reliability of your design. Okay, so in Japan, we have accumulated enough data to analyze the reliability on structural performance. I mean, the structural behavior. But we do not seem to have, I mean, we have a lot of research done, but we have not come to an agreement on how to, I mean, what is the scatter or in loads, especially earthquake loads. If you do not come to an agreement on the scatter of the earthquake loads, then you cannot analyze the reliability of your design. Yeah, I'm not sure if that was clear enough. If you want to do LRFD, you have to look into the you have to analyze the scatter of load and structure performance, structural behavior, both. We have plenty of data on structural behavior, but we don't have, we have not come to an agreement on the scatter of the load. And on top of that, engineers are required to adhere to the loads that are specified by law. Okay, we're stuck on the load side. That is my understanding on why limit state design, or LRFD, has not been established in Japan. Okay, that was my answer to question 1.
Okay, another question is for buildings that exceed the height limit, does the government hire their own engineers to review such projects, or does the government hire other engineering companies that have expertise in such projects to review?
Okay, very interesting question. This procedure is probably, the English term is called peer review or project review or something like that. Okay, in Japan, there are a few, not many, but few companies who are licensed to do this review. Okay, these companies, well, typically hire university professors to review the design. Okay, so the specific answer would be that the Japanese system is that practicing engineers do not review other engineers' design. The professors review these special, the design of special structures. Okay, I'm looking at the next question. What's the reason? Okay, what is the reason for the diminishing popularity of SRC system? Okay, SRC. I'll try to talk more next time. SRC is a system where you first construct steel, and there are many shear studs welded to that steel section. Okay, steel can be erected quicker. So you first construct this flimsy steel frame, and as you go up, gradually you follow by putting formwork around that steel for the beams and columns. The benefit of SRC is that you can go to smaller section compared to reinforced concrete, and you tend to achieve faster construction. So at one point, many buildings of the height between 10 to 20 stories were constructed in SRC. So that was the market of SRC. But now the downside of SRC construction is that you have to have the two trades. You have to bring in the steel people, and afterwards you have to bring in the concrete people. There's a lot of coordination coordination needed, and from the steel fabrication side, it's a lot of work. Okay, you have to put sear studs, many sear studs, on the steel sections. Okay, so that's at least my understanding on why the popularity of SRC is diminished. And what are my thoughts on Nippon Steel buying US Steel? Okay, that was a big news. Okay, but what I read on paper was that Nippon Steel had interest in increasing their capacity to do to recycle steel, because Nippon Steel produces a blast furnace. They are the blast furnace mill company, and I mean, the global interest is pressuring to more green construction, and the blast furnace is viewed as very non-green. So perhaps by lowering the proportion that's done by blast furnace, they can start claiming they're more green. Okay. So the next question is it has okay. Add one more session on damping systems. Okay. Damping systems, that is a very interesting subject, but unfortunately, I'm not as I mean, I don't know damping systems nearly as well as I know steel. Well, I'm sorry. I mean, there are so you might ask Professor Ashwin Kumar to find. I mean, I can talk with Professor Kumar to see whether there is somebody else to talk about damp systems. Sorry, I won't be able to talk about damp structures.
I guess that's all for today.
Okay, there's. Let us do 3 bills regarding. Okay. Utility category for the structure first, and then sizing the members, or vice versa. Okay, this is another interesting question. I mean, that table that I showed you is not very strict on the type of members you can use. So you don't have to use all, I mean, 100% ductile members. Okay, your system may have 80% very ductile members, but you might have a few less ductile members, and you can still be rewarded the highest ductility. So there's some leeway. But my understanding is that engineers have experience, so they start off with a target ductility category, and so my understanding is that more engineers would have start with a target ductility category, and try to size members within that category. So not the vice versa, but the former. Okay. Oh, I hope that was good enough.
Yes, sir, it was better than good enough. I thank you for today, and thank you all the participants for attending the webinar. And we hope to see you next month for another lecture where you'll be covering the construction and fabrication of steel structures in Japan. And
okay, thank you for your participation, and thank you, Devyani.
thank you so much, sir.
Yes.
I'll now close the session.
Okay. Good night. Goodbye.
Goodbye.